Hey, how's it going, everyone? This is the Solid State Workshop with essential and practical circuit analysis. This is going to be a two-part series on circuit analysis, so put on your thinking cap and let's go. So what exactly is circuit analysis anyway? Well, circuit analysis is a toolkit for understanding and designing more complex circuits. So if you want to get into the world of electronics, or you want to understand electronic circuits, well, you're going to need to understand the concepts brought to you in circuit analysis first. And that's because circuit analysis is a layer of abstraction. It is based off of other abstractions, while other abstractions are built off of it. So you can look at this process chart here of how that works. So you start off in physics, and you learn about the electrons and protons and all the small, low-level things. And then you move on to circuit analysis and learn how that works. And then you move on to electronics, which is based off of circuit analysis. And then you can move on to electronic systems, which is based off electronics. So in order to be successful in each area, you first need to understand the area that precedes it, the layer of abstraction before it. All right? Cool. What will be covered in this video? Well, a whole range of topics. We're going to start from the very beginning with some simple circuits, and then we're going to move up into the world of more complex circuits. But along the way, we're going to discover methods which simplify the complex circuits and make performing an analysis on them easier. So here are the topics that we're going to talk about today. We're going to start by talking about linear circuit elements, and then we're going to move on to Ohm's law and series and parallel circuits, which you may have already seen before in a physics class or something. Then we're going to talk about voltage and current dividers, then move on to the big two, Kirchhoff's current law and its associated nodal analysis, and Kirchhoff's voltage law and its associated loop analysis. And we're going to talk about some methods for analysis that are a little more abstract, but are definitely still really cool. And those include source transformation, Thevenin and Norton equivalence, and finally superposition. Today we're going to be dealing with linear circuit elements in all of our examples. And what are the linear circuit elements that we might encounter? Well, we have the humble resistor with units ohm and symbol omega, the capacitor with units farad and symbol F, the inductor with units Henry and symbol H, the voltage source with units volt and symbol V, and the current source with units ampere or amps and symbol A. And now what makes a linear circuit element linear? Well, say we were to write out a relationship between current and voltage for any of these elements, more specifically resistors, capacitors, and inductors. But say we were to write out current as a function of voltage, we would find that the current through these devices, these elements, is going to be a function of voltage times some constant. And so that makes it a linear element because there is a linear operator in that relationship. In a non-linear circuit element, the operator is something like an exponential operator, e to the power of something. But we won't be encountering nonlinear circuit elements today, so don't worry about those. And more specifically, today we're going to be dealing with exclusively resistors, voltage sources, and current sources. Before we go any further, let's discuss the different parts of a circuit and the names we give to these parts. Here's a circuit that we'll use as an example. And now the first part is called a node. And a node is a junction of connecting wires. It's where circuit elements are joined together. So in this case, we have 4 nodes because there are 4 points of connection in this circuit. We have a node connecting the voltage source to a resistor. Here we have 2 resistors and a voltage source connected together. And here we have a voltage source and a resistor connected together. And we also include this big node at the bottom. And every point on this big node is at the same electric potential. And well, how could that be? Well, there's nothing in between any of the points on the node here that could alter its potential, such as a resistor or a source. And if, say, we did add one of those things, well, then this whole thing is no longer a node. Maybe only this part would be a node. Next part we have is called a branch. And so a branch is really just a fancy name for any of the circuit elements between 2 nodes. So here are all our branches in the circuit. It's really as easy as it sounds. It's the element between nodes. I guess the difference between a branch and just a circuit element is that a branch is an element that is part of a circuit by definition, while a circuit element on its own can just be a standalone thing that we can talk about by itself. Alright, so finally let's talk about loops. And a loop is a closed path that begins and ends at the same node. And a loop can't pass through any node more than once. So here we have three different loops in this circuit. We have a small loop here, and we have another small loop here, and then we have one big loop that encompasses the entire circuit. And these are all loops. So try to become familiar with these terms because I'll be using them to describe points on a circuit. And plus you get to sound smart when talking to your friends, so that's a plus. Alright, so Ohm's law, the most fundamentally basic and essential relationship in all of circuit analysis. Now before we talk about the actual equation, let's talk about the variables that it is consisted of. So we have V for voltage, I for current, and R for resistance. And now remember, voltage is an across variable, meaning you take the voltage between 2 points or across some element in the circuit. And I, or current, is a through variable, meaning it's the current through an element. And resistance is simply a constant assigned to a particular resistor. Now, Ohm's law says V equals I times R, I equals V over R, or R equals V over I. So it makes it possible for us to solve for an unknown current, voltage, or resistance, granted that we already have two of those elements of that equation. So if we have a circuit that looks like this with a voltage source of 30 volts and a resistance of 75 ohms, we can determine the current that must flow through that resistor. And that's easy because in this case, I equals 30 over 75, and that equals 0.4 amps. Circuit elements can be connected in two basic fashions, either in series or in parallel. So let's talk about series first. In a series circuit, the elements in a circuit are connected one after another, meaning the front of one circuit element is attached to the back of another element, and the front of that element is attached to the back of another element. That's what makes it a series circuit. In a series circuit, there's only one path for current to flow, and that's because there's only one loop here. Where else could the current possibly flow, and how could it possibly be different at different points in the circuit? So we could test for current here, and it'll be the same as current. The same value for current will be found here, and the same value for current will be found here. Now if we have multiple resistors in our circuit, then we can simplify multiple resistors down to one equivalent resistance. And we can do that using a very simple equation that says R equivalent equals R1 plus R2 plus all the way up to Rn, which is the nth resistor. So in our particular instance, we have a 100 ohm resistor and a 50 ohm resistor in series. So the equivalent resistance that would be formed between this point and this point would be 150 ohms. And now that we know the equivalent resistance, basically we can rewrite these two resistors as one resistor. Then we could solve for the current just as we did previously. So applying Ohm's law, we see that the current is equal to 30 volts, the source voltage, over the equivalent resistance of 150 ohms. So dividing 30 by 150 gives us 0.2 amps. In a parallel circuit, like this one, all resistors share a common voltage. And we can see that because the 30 volt source here is attached across both the 150 ohm and the 100 ohm resistor simultaneously and in the same places. But the difference between parallel and series is that the currents through each of these resistors can be different, and in this case they are different because the values of the resistances are different. So there's going to be less current flowing through the 150 ohm resistor than in the 100 ohm resistor. And say we wanted to find the current up here, the green current. How could we do that? Well, we can turn these two resistors arranged in the parallel configuration into one equivalent resistor like we did in series circuits. And we're going to use this equation, 1 over R equivalent equals 1 over R1 plus 1 over R2 all the way up to 1 over Rn. And so in this case, we find that the equivalent resistance that will replace this circuit block right here is equal to 1 over 150 plus 1 over 100, and then whatever answer you get there, you just flip it. So this arrangement of resistors can be replaced by one 60 ohm resistor. And so therefore we can find what that green current would be. And we're going to use Ohm's law, and you divide 30 volts by our equivalent resistance of 60 ohms, and we find that the green current would be 0.5 amps. Now say we wanted to find the currents through each of the resistors. How would we do that? Well, we would simply divide the source voltage, since both share the same source voltage, by the resistance. So for the pink current through the 150 ohm resistor, that's equal to 30 volts over 150, which equals 0.2. And the blue current through the 100 ohm resistor is equal to 30 volts over 100 ohms, and that equals 0.3 amps. So some takeaways from here. Basically, we can say that the green current flows into this node here, this junction of components, splits. Some of it goes down one chute, and some of it goes down another chute here. And then back at the bottom, and then down at the bottom, these currents recombine back into the green current, and rinse and repeat.